Hi, hello, namaskar. Myself Mr from Department of Physics. As you know, well, dear students, we are in a topic that is nothing but thermodynamics. As you know, under this particular concept, we have studied many concepts like zeroth law of thermodynamics, first law of thermodynamics, and many more concepts. And today, we will discuss one of the most important concept that is called as Carnot engine. Hope you know what exactly the heat engine. That the things which I have discussed in the previous class, that is nothing but it is a kind of device which can used to convert heat energy into mechanical energy. Similarly, your job is to get Carnot engine because it is the engine where we have got its efficiency. In the sense, it is a kind of ideal heat engine. Or what is the use of Carnot engine we can expect over here? The Carnot engine can be used. It is a similar kind of how we have used the heat engine. What do you mean by heat engine, by the way? The heat engine, which is nothing but it is an engine which can convert the heat energy into mechanical energy. Similarly, and today we will discuss one of the most topic, that is a Carnot engine. Basically, this Carnot engine which consists of 4 different parts of its own. The first one, we can expect working substance. What is this? And this is called as we can call it as, that is working substance. It is a substance which consists of diathermic wall and along with the movable piston, somewhat like this. So this is the movable piston which can go up and down with the frictionless. And there is a gas which is there inside this particular chamber over here. By the way, what do you mean by adiabatic wall? It is a wall in which it doesn't allow heat, it can pass through that. Similarly, this base which is having the base of this working substance which is made up of conducting wall. What do you mean by conducting wall? Conducting wall which is nothing but which can allow heat can pass through this. Are you getting? Well. And this the zebra line which I have made over here, which is a representation of a diathermic wall. Okay, and this is a working substance, and this is how exactly it looks. And one more part we have, that is nothing but we can call it as source. What do you mean by source, by the way? The source, which is for a time how the representation of a source over here. The surrounded by this particular source, which is surrounded by one adiabatic wall along with the non-conducting wall at the top over here. And this line which indicates what? Conducting wall. And inside which is maintained at a temperature T1 which is maintained at a very high degree Celsius. That is called as source. And one more we have, that is nothing but a sink over here. So what is this? This is nothing but a sink, and sink also which is maintained at a very low temperature. Let us call it as T2 over here. T2 is the temperature which is maintained at a very low temperature, and this representation is like this is surrounded by the 3 different parts of the sink, which is surrounded by diathermic wall, and the top of this wall which is made up of conducting wall. And this is what exactly we can have under the concept of sink over here. And one more we have, that is nothing but non-conducting stand. What do you mean by this? This is called as non-conducting wall. Well, so this is what exactly we can have. It is a non-conducting wall over here. Are you getting? Non-conducting wall is what? It is a kind of diathermic wall over here, which means all the 4 sides of this particular wall which is surrounded by insulating medium. It is a non-conducting medium which doesn't allow a heat can pass through this. So this is what exactly we can have, that is in terms of non-conducting stand. Are you getting? Well. And this is one concept we can have. And one more thing, basically this Carnot engine of its work done, we can expect there are four different processes we can expect under the concept of the Carnot engine. Along with us, we will try to have one pressure versus volume diagram, that is nothing but a PV diagram. So let us take this is the pressure and the volume, and the first process we have, that is nothing but isothermal expansion. First one we have, that is isothermal expansion. Which is the first one? Isothermal expansion. Now, what comes to your mind when I say expansion? What is the first term which comes to your mind when I say expansion? When the object is going to expand, what happens? Don't you think its volume is going to increase? Don't you think its pressure is going to decrease? Similar kind of scenario we are going to deal over here. Now, your job is to take this as a working substance, it does some work. How? We'll get to know. Now, this is a working substance. Your job is to take this whole setup and your job is to keep it upon the source over here. Now, if I keep this whole setup over source over here, what happens? Obviously, the source which is maintained at a very high temperature, yes or no? So, this source which is maintained at a very high temperature, as a result, what happens? Don't you think there is an expansion will take place, because here we have a conducting wall and here also there is a conducting wall. So what happens? There is a increase in heat will take place, which means heat is going to transfer from where to where? T1 to this particular gas molecule over here. So then what happens? This piston starts moving in upward direction. Got it? Well, so what happens in isothermal expansion? Since it is isothermal, what parameter remains constant? What do you mean by isothermal process, by the way? It's a process in which temperature remains constant. To maintain a constant temperature, which are the parameters are varying over here, that is pressure as well as volume. Which means here, which is the initial pressure which is maintained, P1 V1 2, that is P2 V2 at T1 as a constant. So this is what exactly we can expect under isothermal expansion. Now, what is the work done we can expect over here? So what is the work done? It's the work done which is equal to integration of your volume is varying from where to where? V1 to V2. So that what is the lower limit I can expect here? That is or this is also which is W1 which is equal to Q1, because the Q1 amount of heat which is absorbed by a source, which is equal to, that is V1 to V2 into PdV, which is equal to, what is the work that we had for an isothermal process over there that we have discussed in a separate derivation part. So this was the end product of that particular derivation. Yes or no? Yes. So now your job is to take, that is the R, T can be replaced by what? What is the temperature which is maintained over here? It's very simple. That is a T1. This is a LAN which indicates lock to the base T. Okay. So this is called as LAN of V2 divided by V1, which means here work is done by the system, so that this work done is positive over here. Are you getting? So work is done by the system in the sense what? Piston is moving upward in direction. Understood? Well, so this is what exactly we can have. It is a T1 which represents what over here? It is a temperature, and V2 by V1. Similarly, along with this, your job is to plot one graph over here. What is the graph we can plot over here? It's very simple. I can expect, as you know, as the pressure increases, as the volume is increases, don't you think the pressure is going to decrease? As this piston is moving upward in direction, can I expect there is a decrease in pressure will take place? So we can expect curve somewhat like this. That is nothing but the started with the point A, that is the P1 V1 to point B, that is P2 V2. This is the point where we can expect the pressure and volume which is moved from P1 to P2 and V1 to V2 with the constant temperature as T1 over here. Okay, well, and the next process we have, that is nothing but adiabatic process. That is nothing but, this is the first one. The second one we have adiabatic expansion. Adiabatic expansion. And what do you mean by adiabatic process, by the way? It is a process in which heat remains constant. To maintain a heat, we need a insulating wall. Among these three, which is having insulating wall, which is having insulating the medium, this is an insulating medium between a working substance with respect to this particular part over here. Now, your job is to take this whole setup, this whole working substance, and your job is to keep it over here. And if I keep on the top of this non-conducting wall, what happens? Do you think heat can transfer from here to this particular case? No. So this is a process in which temperature is going to vary, but heat is not going to exchange between system to surrounding. So similarly, we can expect P1, this is the pressure can vary from where to where? P2 V2 to, that is P3 V3. Are you getting? So P3 V3, as well as a temperature is also varying from, that is T1 to T2. Also temperature varies from where? T1 to T2. So because it is a adiabatic process, temperature will not remain constant. So that's why we can have, that is W2, which is equal to integration from where to where? Your volume is varying from where to where? Initially it was having a volume V1, V2, then which is moved to V3. So we can expect V2 to V3 into P into dV. This was because pressure into change in volume we can expect. That's why. Which is equal to, what is the relation we have got with respect to the work done in adiabatic process? It's very simple. It's R is the universal gas constant, gamma which deals with what? Gamma which deals with specific heat ratio. Well, so this is what exactly we can have. R divided by gamma minus 1 into T1 minus T2. So this is what exactly we can have in adiabatic expansion. Now, the one more process we have, that is nothing but, along with this we will try to plot one graph over here. What is the graph we can plot? So this is and one more thing. Do you think this adiabatic curve is steeper than isothermal or greater than this? According to our previous class observation, we have proved that your adiabatic curve is steeper than isothermal curve, which means if I want to plot a graph versus pressure versus volume, I can expect a steeper curve somewhat like this. Got it? So this is the point C where pressure and volume varies from where to where? P2 to P3, V2 to V3. Well, so this is what exactly we can have, P2 to P3 and V2 to V3. Understood? Okay. And the next one we have, that is nothing but isothermal compression. That is isothermal compression. Well, so this is the isothermal compression we have. What do you mean by compression, by the way? Compression, which is nothing but what? Which is going to compress. When any object or any gas is going to compress, what happens? What are the parameters are going to change? Obviously, pressure increases, volume decreases. Correct? If volume decreases, obviously pressure should increase. It is a common factor that we know. Now, how I can decrease the volume as well as increase the pressure? How I can do? Now, we need to hold a substance so that it can decrease its temperature. Well, so your job is to take this working substance and your job is to keep it on the top of a sink. Sink, what do you mean by sink, by the way? Sink, it is a part in which is maintained at a very low temperature than a source over here. Now, if I keep this whole setup or on the top of a sink, what happens? Don't you think this particular movable piston will move downward in direction so that work is done on the system or by the system? Obviously, work is done on the system, which means work done is going to negative according to our sign convention. Okay? So, and one more thing, since it is isothermal compression, temperature remains constant. Remember this particular point. Whenever we have a isothermal process, its temperature remains constant. Whenever we have adiabatic process, its heat remains constant. Understood? Well, since we have isothermal compression, your job is to keep working substance on where? On the top of the sink. If you keep on the top of the sink, what happens? Your piston is moving downward in direction, or as a result, work is done on the system. So now, your pressure and volume varies from where to where. Initially, it was P3 and P3. So now, it can vary from P3, V3 to, that is the P4, V4, by keeping T2 as a constant. Because the temperature is varied from T1 to T2. Now, right now, T2 we have maintained as a constant. So, if it is so, what is the formula? What is the work that we can expect? That is very simple. That is W3 which is equal to Q3 which is equal to R into T2. The ln of here V3 by V4 comes into the picture. Why can't be V4 by V3? It is as simple as because work is done on the system means a minus comes over here so that it becomes what? Logarithm or log of E of V3 minus log of E of 4 over here. So that's why. Because plus into minus minus, so that's why V3 by V4 comes into the picture. Okay? Well. So this is what exactly we can have under the concept of isothermal process, isothermal compression. To get a compression, what we need, we have kept a working substance on the top of a sink over here. Understood? Well, and one more thing we are supposed to go with, that is nothing but the fourth one we have, that is adiabatic compression. That is adiabatic compression. So this is what exactly we can have, adiabatic compression. What do you mean by adiabatic compression? Now, since it is adiabatic process, where I supposed to keep your working substance? Since there should not be an exchange of heat between a system and surrounding, to follow that procedure, I supposed to keep this working substance on the top of a non-conducting stand, so that we can say that there won't be an exchange of heat between a system and the surrounding. Understood? So this is what exactly we are supposed to do. Now, especially in adiabatic process, there would be a chance of increase in temperature or decrease in temperature. But before that, we are supposed to plot a graph which is based on isothermal compression. So what would be the graph we can expect? So obviously here pressure increases, volume decreases. So now this is a process in which the pressure increases, volume decreases. Since it is isothermal curve, I can expect a somewhat like this. Understood? Okay. So this is the point D, I can say, that is a P3 to P4 and V3 to V4 I can have. Okay. Well, so this is what exactly I can have. And one more concept, that is adiabatic compression, where we are supposed to keep your working substance on the top of a non-conducting stand. so that there won't be an exchange of heat over here. So if it is so, your pressure and volume varies from where to where? P3V, that is a P3V3 to, again it goes back to its initial position, which means again it goes back to P1V1 with the temperature of T2 to T1. So don't you think this looks like a cyclic process over here? So now what would be the work done we can expect over here? The work done is very simple. W4 which is equal to, that is a R by gamma minus 1 into T1 minus T2. Why can't be T2 minus T1? Once again it is the work is done on the system. So that's why minus sign is comes in the picture, so that if I multiply inside the bracket, what happens? Once again it becomes T1 minus T2. So this is what exactly we can have over here. So if it is so, what is the graph we can plot over here? Obviously we know that is the adiabatic curve is steeper than isothermal curve. I can expect somewhat like this. So this is the point where it has reached to once again its initial position, which means initially it has started from P1 V1, then to P2 V2, then P3 V3, then P4 V4, and then once again it goes back to P1 V1. So this is what exactly we can expect under the concept of Carnot engine. Well, so these four are different parts of Carnot engine where we are supposed to remember, and these four are initially isothermal expansion. Means how to get isothermal expansion? Your job is to take your working substance and keep it on source. How to do adiabatic expansion? Once again you are supposed to take this working substance and keep on the top of non-conducting stand. Why? Because adiabatic process is a process in which there should not be an exchange of heat. That's why. And if you want to get a compression, where is supposed to take? Your job is to take the same working substance and keep it on the top of sink. Because sink which is maintained at a very low temperature, so that piston moves downward in direction. So that there is a decrease in volume will take place, increase in pressure will take place. That's why the graph goes now in this order over here. And if you want to get adiabatic compression, your job is to take working substance on the top of a non-conducting stand, so that there is a small decrease in volume will take place by increase in pressure will take place, so that it can reach up to its initial position somewhat like this, where it was. Understood? Well, remember these four processes of Carnot engine. Okay, fine. Well, we'll try to have eye on the topic, that is efficiency of heat engine or Carnot engine. Well, by the way, what do you mean by efficiency? So before we get the efficiency, we are supposed to get what is the total amount of work done in the particular cyclic process. It's very simple. That is the W is equal to, we can say W1 plus W2 minus W3 minus W4. So this is a process we had. Now if we substitute all the values over here, we can expect we had W1, W2, W3, W4. Now if I substitute the value of W2 and W3, it will get cancelled out each other. What is remaining over here? The remaining thing is that is nothing but this will get cancelled. Then W which is equal to what is remaining over here, that is R T1 ln of V2 by V1 minus R T2, that is the ln of V3 by V4 is remaining over here. Correct? No? And also this looks like W which is equal to, that is a Q1 minus Q2. Okay, so now what do you mean by efficiency? By the way, efficiency which is nothing but eta which is equal to, that is the work done divided by heat absorbed. that is the heat absorbed. So altogether what I can write, W divided by heat absorbed is Q1, which is equal to W can be replaced by what? By using this star equation, that is equal to Q1 minus Q2 divided by Q1, which is equal to 1 minus Q2 by Q1. Now this is eta, where eta is equal to what I can write, that is 1 divided by Q2 can be replaced by this much, that is R T2, that is the ln of V3 by V4 divided by R T1 ln of V2 by V1. So this is what exactly we can have over here. Now R will get cancelled, what is remaining? T2 by T1. Now the job is to make in such a way that these two terms should be equal so that it can get cancelled out each other. Now we'll do one thing. You try to look into this PV diagram which we have got over here. Now we have started up with at a particular point A, P1, V1 with respect to T1, which is moved to with respect to T1 only. So this is a process we can expect under isothermal process. In isothermal process we can have, that is the P1 V1 which is equal to, that is the P2 V2, yes or no? So this is the first process we had with respect to A to B. Now when we moved from B to C, we had a P2 V2 T1 2, and here we had a T1 to T2, which is nothing but adiabatic process. Whenever we have adiabatic process, we had one equation in terms of gamma relation, that is P2 V2 gamma is equal to P3 V3 gamma, yes or no? So this is one more relation we can expect under adiabatic process. Then which has moved from P3 V3 T2 to P3 V4 T2. Because it's the isothermal process, what is the ideal gas equation we can expect? That is P3 V3 to P4 V4. P3 to P4, P3 to V4. Now once again it is the adiabatic compression we had, we can write, that is P4 V4 gamma is equal to P1 V1 gamma. So now what I do here is that I will multiply each other so that I can expect, that is I will multiply all those things, that is P1 V1, that is P2 V2 gamma, and P3 V3 into P4 V4 gamma, which is equal to what I can write. I write all those things, that is P2 V2 into P3 V3 gamma into P4 V4 into P1 V1 gamma. Are you getting? Which means all P1 V2 P3 will get cancelled. What is remaining over here? The remaining thing is, that is V1 V2 gamma, V3 V4 gamma, which is equal to, that is similarly V2 V3 gamma, V4 V1 gamma. Now we bring to the other side, it becomes what we can have, that is can I write this? Looks like V2 gamma minus 1, also V4 gamma minus 1. When you bring to the other side, what happens? It is V3 gamma minus 1 and V1 gamma minus 1. Now gamma minus 1, we have common in the power over here, so that it will get cancelled out each other. So what happens here? That is V2 V3 which is equal to V3 which is equal to V1 by this. So now what I do, can I write this? It looks like V2 by V1 which is equal to V3 by V4. Now if I multiply both sides ln, so this looks like ln of V2 by V1 which is equal to ln of V3 by V4. So don't you think there is an equation which proves this will get cancelled? So according to that particular relation, this will get cancelled. What is remaining over here? The remaining thing is eta is equal to 1 minus T2 by T1. So this is the efficiency for Carnot engine. So this is what exactly we can have in terms of the efficiency of Carnot engine. Similarly, we had for 18 that is 1 minus Q2 by Q1. Okay, well, thank you very much. We'll see you in the next class.